So we'll be starting off with probability. Probability in itself is a very interesting area of mathematics. Probability for mathematics is a vertical where events are assessed. Okay, the events are assessed in a way that the likelihood of something happening, right? The likelihood of something happening is assessed. If it is more likely to happen, it would have a higher mathematical value. If something is less likely to happen, it would have a lesser mathematical value. Okay, that sort of a value can be expressed in simple numbers or in fractions or in any other mathematical operation that is available. Okay, so probability is nothing but checking off the likelihood of any event occurring. Okay, so if an event is supposed to occur, it would have a higher probability. If it is not supposed to occur, it might have a lower probability or a zero probability. If there is, if let's assume that there is the probability of one event occurring is equal to 1. Okay, 1, the mathematical number 1, that means in all likelihoods the event would definitely occur and it is inevitable. You cannot stop it. And if the probability of an event occurring is 0, that means that that event would not occur. Okay, the event would not occur no matter how hard you try. Right, so this is pretty much about the entire probability. It all lies between 0 and 1. Okay, it all lies between 0 and 1. Now we have a few standard areas which we need to discuss. We have to discuss a few standard areas of probability and the few definitions. So probability, whatever would be asked in the exam, would be rotating around coins, would be rotating around dices. Okay, dices, 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 or there's nothing called dices, it is called dice, dies, dice. Okay, it's not somebody's dying, but multiple of dice is dice. Okay, dice, dies. Then about cards and some random objects. Okay, some random objects, maybe something is put in a bag and when you take it out you have to tell the probability of how good a chance there would be of that object to be present or that object to appear outside. Okay, so that is pretty much where it all will be rotating, and this is how we'll be proceeding ahead. There are a few definitions which I would want you to know. The problem is that in the upcoming examinations it has been seen that direct definition questions comes up. I'm not asking you to remember any sort of definitions. The only thing I'm requesting and really pleading to you is to understand the definition correctly so that you can at least rule out the definitions which are not correct. Okay, it will be highly impossible for you to learn the definitions of everything which comes up in mathematics, because that will be a detailed like a proper detailed event in itself. So just understand the concept and come and be in the flow with me. The first one being an experiment. Okay, in an experiment you are basically trying to attempt something. Okay, there is an hypothesis. When I say an hypothesis, it means that you're thinking about something that it might occur. So you take a step forward and you do the action. An experiment is nothing but an action which you have in your mind and you're now performing it. Okay, so an experiment is an action, it is an activity or a process that results in an outcome, and that action is definitely going to give an outcome, be it pass or be it fail. Okay, the pass can be success and the failure can be failure. Okay, there is no shying away from it. You are ready to accept both the outcomes. Secondly, what is an outcome? An outcome is a result, is a result which you are expecting and which you are also not expecting. Okay, it is both expected and unexpected. Both sort of results would be available, both sort of outcomes would be there. Okay, so let's assume that for you're going to roll a die. Okay, you're going to throw a die or roll a die. So for that particular die, what would happen is that the outcomes are 1, 2, 3, 4, 5, and 6. You have not yet selected what is your favorable outcome, but whatever is expected and whatever is unexpected would come out in the outcome. Thirdly, there is something called sample space. There is something called sample space. Sample space is the main focal point. Okay, this is a focal point of the entire probability chapter, and sample space is something which you need to determine beforehand. Okay, you need to determine beforehand that what a sample space means. So the determination of sample space is very vital for you to solve a question. It is basically all possible outcomes. Okay, it is basically all possible outcomes of an experiment. When I say all possible outcomes, this basically helps me to understand that where I am lagging and where what is needed. Okay, and everything that is available which will be given to you after the performance of the experiment, all the possible outcomes. Okay, so let's assume when I'm throwing a die, I'm throwing a single die. When I throw a single die, I would get the outcomes as 1 2 3 4 5 and 6. So that is a sample size or a sample space. When I talk about throwing two dice, okay, throwing two dice, then the outcome would be the first one can be 1 and the second one can be 1 as well. So this is one complete outcome. For a die, as there are six possible outcomes and two dice are being thrown, so 6 square is nothing but 36. So we will have 36 possible outcomes. When I write down those 36 possible outcomes, that would be called my sample space. Okay, I would be accelerating you to the point where all the outcomes of throwing two dice are written. Okay, and then I'll come back to the first page. I'll just show it to you once. Can you see this? This is the sample space when we are throwing two dice. This is the sample space when we are throwing two dice, 1 comma 1, 1 comma 2, 1 comma 3. The first one being constant, the second one being variable, and the second one being constant, and the first one being a variable. Okay, okay, this is just a figurative speech which I used. You have to understand that this is the first dice and this is the second dice. Okay, coming back to the beginning of the chapter, we were here. Now, the fourth point is an event. Okay, the fourth point is an event. It is basically a sample space. It is part of a sample space. Okay, it's a part which you have chosen from the sample space. Let's assume that you said that all the numbers which I want while rolling the die should be even. Okay, this is not an even number, this is an even number. Example is that we're getting an even number when we are rolling a die. So 2 comma 4 comma 6, all of them are even, and the total number of numbers or the total set of observations which we would receive from the sample space would be 6 in nature, because when we count from 1 to 6, 1 2 3 4 5 6, so 6 is basically the number of observations we'll be getting. 1 2 3 4 5 6, we have 6 observations which will be coming down. So the total number of observation goes in the denominator, and the observation which you want or the event which is favorable to you comes in the numerator, which is finding the number of events. Okay, the number of outcomes would come in the numerator. These are the favorable outcomes or the positive outcomes, and this would give me the probability, which is equal to 1 by 2. Coming down to the answer of probability, probability is the measure of likelihood of an event occurring. Okay, the measure of the likelihood of an event occurring is called probability. The probability of rolling a 3 dice, okay, the probability of getting a 3 on rolling a dice which is of 6 side is 1 by 6. Okay, how did I calculate it? The sample space of my die is 1, 2, 3, 4, 5, and 6. Out of that, I just need to get 3. The 3 can occur only once out of the 6th time I am rolling the die. Okay, you'll ask me, if I practically roll a die, then I can get 3 multiple times. If I roll it for 6 times, and I can get 3 twice. But in this case, we are assuming that all the numbers are equally probable to come on the die. Okay, all numbers are equally probable to come at the top of the die. So that is very important for you to understand. What is a complementary event? First of all, we've talked about event over here in point number 4. Then we'll be talking about complementary event. A complementary event is something that happens when the original event does not occur. Okay, let's assume let's assume that you are a sincere, very sincere student. Okay, a very sincere student, the probability of you learning at school is A. Okay, the probability of you learning at school is A, and the probability of you not attending school and still learning at home is A bar. Okay, this is denoted by bar. If you'll study at home and if you'll study at school, when you unite both the options, you are going to towards unity, or you're going towards 100%. So this unity is 1. Okay, this is not unitary, this is unity. So unity is 1. So the possibility of something happening according to you which is positive, and something not happening, or something according to you being negative, if both the probabilities occur together, then the sum of these probabilities is equal to 1. Okay, the sum of these probabilities is equal to 1. This is very necessary for you to understand. We will be demolishing multiple questions using this concept, using this very easy concept that something happening and something not happening. We will be demolishing multiple questions using this concept. Okay, you'll see that, let's assume that we are tossing two coins. Okay, we are tossing two coins separately. When we are tossing those two coins, we will get a sample space of heads and tails. Okay, we'll get a sample space of heads and tails. I As soon as I find a little space, I'll just talk about it over here. Okay, we are tossing two coins. The possibility of the first coin and the possibilities of the second coin. The first coin can have two possibilities of it being heads or it being tails. The possibility of second coin after being tossed are again two, heads or tails. So the possible outcome here would be head comma head. Then the first one can be head, the second one can be head. Keeping the first one constant being head alone, the second one can be tails. Similarly, keeping the second one constant, keeping the first one, okay, the keeping the first one has to be tails. The second one can come out as head. Similarly, keeping the first one tails, the second one can also be tails. Okay, so this is my sample set, or this is my sample size. Okay, sample set, sample space, sample size, all are synonymous. Synonymous. Okay, all of them are synonymous. So all these four are the possibilities which can occur to me. Got it? When I talk about these possibilities occurring, there was this thing that I said, that let's assume that no tails comes into the picture. Okay, no tails comes into the picture. When I say that no tails come into the picture, what I mean is all heads are coming into the picture. Then I will have to count all heads or at least one head coming into the picture. So for that, there is 1, there is 2, there is 3. The probability of no tails coming into the picture, or probability of no tails coming into the picture, would be 3 upon 4. Okay, 3 times the occurrence of heads. Just a second, just a second. No two tails, basically. I'm talking about no two tails coming together in the picture. So when two tails are coming together, that is only one probability. When only heads or heads along with tails is coming, that is also my favorable possibility. So when I have to count, these are just 3 out of 4 which I have to count. There is a possibility that the sample set size, or the sample space size, is 64 or 216, or maybe even bigger. Then it will become very difficult for you to count. So it is better that you know that the probability of tails, or of tails occurring twice together, and the probability of tails not occurring twice together. Okay, not occurring twice together. When both of them are added up, let's assume this is x. So the probability of both of them when they are added up, 3 by 4 plus x is always equal to 1. When I talk about x, the value of x is nothing but 1 by 4. So the probability of tails occurring together is only once out of 4 times. So instead of counting, you can use this formula. Okay. This is the other way of reaching the outcome pretty easily or pretty quickly. Okay. Now going back to the point where I was. I'm talking about independent events now. Okay. We're talking about independent events now. When two events do not influence each other, they are called independent events. And also, the occurrence of one does not affect the occurrence of the other. The occurrence of one does not affect the occurrence of the other. So the example is rolling of a coin and rolling of a die are usually independent events. Okay, you're rolling a die over here and you're flipping a coin. Okay, flipping a coin and rolling a die, these are two different events, two separate events, so they are called independent events. Further further there are some events called dependent events. Okay, there are some events which are called dependent events. Independent, sorry, when I talk about, when I say independent events, you are going to get confused if I'm talking about independent events or independent events. Okay, what I mean to say is, when I talk about dependent events, then the occurring of the first event would definitely be harming or affecting, be it positive, be it negatively, would be affecting the other event. Okay, like the example is very beautiful: drawing the card from a deck without replacement. Okay, drawing the card from the deck without replacement. What would happen is, when I draw a card and I don't keep it back, in a deck there are 52 cards. Okay, this is my sample space, that 52 cards are available. When I draw a card and I don't replace it back, then my sample space comes down, my sample space becomes 51. So this changes my entire equation. Okay, this changes my entire equation. So these are dependent events. When you do not place back the card after taking it out of a deck, then the next event which is going to occur is going to get influenced by the first event that got occurred. Then I talk about conditional probability. Okay, I talk about conditional probability. The probability of an event given that another event has occurred. That another event has occurred. Let's assume that you've already eaten food. Now you're going to sleep. Okay, so your mother is going to tell you that if you have already eaten food, then you can go to sleep. So the probability of you eating food is a different ball game, and the probability of you sleeping is a different ball game. Okay, but these two events are interconnected because from the past patterns, it has been seen that whenever you eat food, you feel sleepy. Okay, so there is a conditional probability involved in it. There is a conditional probability involved in it. Conditional probability is a little bit of a advanced event, an advanced chapter, so you need not worry much about it, but definitely when the need be, we will be talking about that as well. Okay, so moving directly to the questions. No, a little bit more about probability and then we'll be moving towards the questions. Okay, when I talk about the probability of an event, then I will be talking about the number of events that happened which were falling in my favor, and the total number of trials which took place. Okay, the total number of trials which took place would be divided by the number of events that happened. So the probability of any event happening is equal to m upon n. M being the occurrence of favorable events. Okay, and then the probability of all the events should be divided by it. Okay, probability of all the events, or the number of all the events, or the number of all the trials which are occurring would be put in the denominator. Okay, the probability is nothing but m upon n. N would mostly be greater than m. Okay, and there would, I shouldn't even write mostly, it would always always be greater than or equal to m. Okay, this is a short reason. The reason being that when there are total number of occurrences, then only you will be able to check which of them are favorable. Okay, if you throw a biased coin, okay, which would only and only show heads, and you ask me what is the probability of head turning up, then I would say the probability of head turning up is always, which is also equal to 1. Okay, okay. So the probability of any event occurring, E is equal to m upon n, where m is the number of favorable events which occurred divided by number of n's, or the total number of experiments which occurred. Okay. Also, there is a concept of non-occurrence of an event. Okay. There is a concept of non-occurrence of an event. I've already talked about it over here. When the event occurs, it's called E. And when the event does not occur, it is called E bar. E bar. It's also called E naught. Okay. E bar and E naught. Okay. And the event not occurring, when the event was occurring, it was occurring m times. When the event was not occurring, it was occurring n minus m times. Okay, it was occurring n minus m times, n minus m times. Okay, this is the event not occurring. So n minus n occurrences are not favorable. Okay, all the occurrences which are happening not in my favor are not favorable to me. As simple as that. Okay, so the probability of E naught, or the probability of E bar, is equal to n minus n whole upon n. Secondly, the probability of E occurring and the probability of E not occurring, when they are added up, they would always sum up to be 1. Okay, they would always sum up to be 1. Also, the probability of E occurring can be 0, but mostly would be above 0. Also, the probability of E occurring could be 1, but would mostly be above 0 and less than 1 only. Okay, so this is a very strong and important point which you must remember. In the exams these days, they give conceptual questions, and this question might be their upcoming favorite. Okay, and I'm going extremely slow. I'm just really wanting and really thinking that you must understand each and every point and each and every basic of probability before I jump on to the questions. Okay, I think everybody is pretty ready now, and we can move to the questions. The probability of certain event happening is 1. The probability of certain event not happening is 0. Okay, impossible event and certain event. Probability of E is equal to 1. The probability of event happening is equal to 1. That means it is a certain event. And the probability of E not happening, or the probability of E being equal to 0, that is called an impossible event. Okay, I have already talked about it, and this is one of the examples which I took from the last slide. That's why I had to come here. Moving to the basics of probability, and this is our first question which we'll be discussing. The coin is tossed 1000 times with the following frequencies. The following frequencies means this is the output. This is the output which we are talking about. Heads came 455 times and tails came 545 times. So what is the probability for each event? Okay, so what is the probability for each event is the question. So first of all, the main point which I need to find out is my sample space. As I've already talked about the sample space in the definitions, sample space is all the occurring events. Okay, all the events which occurred, or all the total number of tries which took place. So the total number of trials which took place was 100. Sorry, 1000. Okay, 1000. 1000 was the number of times the coin was tossed. 1000 times the coins was tossed. So T is equal to 1000. Further, I need to compute the probability for each event. There are two events that are taking place. The first event being E1 and the second event being E2. Assuming that event 1 is the occurrence of head, so the probability of heads need to be found out. The event 2 saying that the probability of tails need to be found out. So when I talk about the probability of heads, the probability of heads, the probability of H, or means the probability of heads coming, is the first of all we're going to check the number of times head has come. So head has come 455 times, and the number of times tail has come. The tails has come 545 times. So for each event, we first need to know the favorable outcome, which is 455 over here and 545 over here. These are the two favorable outcomes of separate events. And after that, so both the events separately are favorable. Okay, they are favorable separately. So 455 is the first favorable events possibility. So 455 divided by the total events or the total sample space. The sample space which we have is 1000, because 1000 tries were taken. Okay, so the answer over here is 0.455. Similarly, here 545 is the favorable event, the possibilities or the number of times the favorable event has occurred, divided by the total number of tries which have taken place, which is 1000. So 545 divided by 1000 would be 0.545. Okay, so really cool thing, or something which we have already discussed, I'll prove it over here. If you add both of them, you would get to know that the probability of both the events occurring simultaneously, or both the events occurring are complementary to each other, which is also equal to 1. Okay, so they complete each other. They complete each other. So this is the entire story, which I was telling, and I have proved it right over here. Moving on to the next question. If the probability of cornering, or basically is nothing, it's not cornering, it's winning. If the probability of winning a game is 0.73, what is the probability of losing it? So the probability of winning a game plus the probability of losing a game is equal to 1. Okay, winning and losing, and winning and losing are complementary events. Okay, they complete each other, or they complement each other. Okay, they complete each other, they are complementary events. So the probability of winning plus the probability of losing would be equal to 1. So the probability of losing has been asked, and the probability of winning has been given as 0.73, plus the probability of losing is equal to 1. So the probability of losing according to this scenario would be 1 minus 0.73, which is equal to 0.27. Okay, 0.27, and this is my answer. Got it? Moving to the next question here. If the letter of the word Ramanujan is put in a box and one letter is drawn at random, find the probability that the letter is A. Okay, so I'll write all the letters separately. RAMANUJAN. Okay, first of all, I'll find out the T, or the sample space. Okay, the sample space. What is the, if I pick one, then how many would I actually have to pick so as to complete the set which I have over here with me? So the length would be 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so we would have 9 as the sample space. After having 9 as the sample space, I would be moving to my most probable event, or my favorable event. So my favorable event is equal to the occurrence of A. Okay, my favorable event is the occurrence of A. So how many times has A occurred in Ramanujam? The answer is 1, 2, and 3. A has occurred thrice in Ramanujan. What is the total length of Ramanujan, or the total number of letters in Ramanujam, which is equal to 9. So 3 by 9, or 1 by 3 would be the probability of occurrence of letter A in the word Ramanujan. Okay, in the word Ramanujan. Ramanujan. Cool. So this is my answer over here. Moving to the next question. Now this question is pretty solid. Okay, Do listen to it. And this was asked in the mains examination of, I think, 2022. The question says the probabilities of solving a problem by three students are, say, 3 by 7, 5 by 9, and 1 by 5, respectively. The probability that the problem would be solved is what? Okay. So, first of all, I'll be writing down all the facts that I have. This is the probability of the problem being solved. The first probability of A, then B, and then C. For A, the probability is 3 by 7. For B, the probability is 5 by 9. And for C, the probability is 1 by 5. Now, the probability of the event not occurring. Okay. The probability of the event not occurring or the problem not being solved would be 1 minus 3 by 7, which is equal to 4 by 7. 1 minus 5 by 9, which is equal to 4 by 9. And 1 minus 1 by 5, which is equal to 4 by 5. So, the problem being solved is here, and the problem not solved. So, separately, the thing has been, now the thing is now available with you. Okay. So, I'll be talking about solving the problem now, solving the question first. Okay. The probability that the question is solved. If I take this route, I'll show you. If I take this route that the problem is solved in the first case, so A also solves it, B also solves it, and C also solves it. Okay. In this way, the problem has been solved. But in the case that only A solves it and B and C don't solve it, this is also a favorable outcome of mine. Similarly, if B solves it and A doesn't solve it and C doesn't solve it, again a favorable outcome for me. For C solving it, A not solving it, and B not solving it. Similarly, if A and B are solving the problem and C is not solving the problem. Similarly, A is not solving it, B and C are solving it. Similarly, um, which one? B isn't solving it, A is solving it, B is not, and C is solving it. So this basically becomes a very long problem. Okay, this becomes a very long question, and if you get this question in the examination and you use the straight approach, you would not be able to get the correct answer out of it. Okay, there is one route from which you would get the correct answer. I think I'm missing out on one. No, these are three, this is 7. Yeah, so there is one thing which we are missing out on. In the second possibility, if I say that A is unable to solve it, B is unable to solve it, and C also is not able to solve it. A not able to solve it, B not able to solve it, and C also not able to solve it. This means that the problem was not solved. On the flip side, if I remove this, if I remove this from my equation of solving plus not solving equal to 1, then I would be able to get this answer. I'll repeat. I have the probabilities available with me of each and every person. If I take the straightforward route and I check how the problem would be solved, it is going to be a long run. Okay, it is going to be a long run. But if I take a shorter route, the shorter route says that the problem is not solved. As simple as that. If I subtract, if from 1 I subtract that equation which says that the problem is not solved, I would reach a conclusion which would say that the problem has been solved, which is favorable for me as well. So let me take you through that route. For A not solving the problem, the probability is 4 by 7. Similarly, for B not solving the problem, the probability is 4 by 9. And similarly, for C not solving the problem, the probability is 4 by 5. When I multiply all of them together, my answer comes out to be 45 upon 315. This is the possibility that the problem is not okay. The problem has not been solved. But if I subtract this not solved from 1, 64 upon 315, my answer comes out to be 251 divided by 315. And this output is nothing but the problem being solved. Okay, this output is the probability of the problem that is solved now. Okay, instead of taking the long route, you can always follow this method of the complementary property of probability, which simply says that an event occurring in my favor versus the event not occurring in my favor, when both of them are added, when both of them are added, then I would not I would not be in a hurry, I would not be in a problem, and I would be given the answer as 1. Okay, I have used that property, took the reverse route, and here I got my answer. It's as simple as that. Okay, so I'll be moving on to the next question. Now we're talking about coins. Okay, now we're talking about coins. We are using a 5 rupee Indian coin of the year 2000, a 24-year-old coin. I believe most of you people would be having it with you as well. A coin has two faces, and the probability of after one flip head coming and the probability of after one flip tail coming is equal. When there are two situations where we do not consider there to be a fair luck game, that is, if the coin is biased. Okay, if the coin is biased, I would not take it into consideration. Secondly, if my coin falls still, okay, falls still, or it is standing, okay, a standing coin, I would not take it into consideration. When is my coin biased? Let's assume that the weight of the coin has been calibrated in such a manner that most of the times it would be flipped. It would give me an output of heads. Okay, so the coin has been biased towards heads, so we would not take that into consideration. When is the other case? Okay, this is the case of weight being added to the coin. And what about the second case? The coin would remain biased. The coin would remain biased when both the faces are the same. Both faces are the same. When does that happen? When you wish to, let's assume, you wish to unfairly win a battle or you wish to cheat. So that's when you take the coin which has the same faces. So these are the two cases when you are not in a fair game, or luck would not be on your side, it might be in your opponent's side. So these two cases would not be taken into consideration. It should be an unbiased coin. And when I say unbiased coin, it is equally probable to get a head heads or tails. Okay, it's equally probable to get a heads or tails, that is for sure. Okay, Moving ahead, there is the concept of sample space. Okay, I am going to tell you the concept of sample space over here first. As I've already said, that sample space is the the entire area which would come as an output to me. Okay, or the total number of attempts that are taken. The total number of attempts that are taken. Okay, so let's assume the coin was flipped once. Okay, in one flip you would get an output as heads or tails. Simple. If we take up two flips, the output is going to be heads heads, tails tails, heads tails, and tails heads. Okay, okay, so we have it pretty clear over here with us. If the coin is flipped thrice, what would happen? Heads heads, tails, head tails, head tail, head head. Okay, similarly, tails tails tails, head head head. This is okay, this is head head head, triple head. And then we would have TTH, THT, and I think this is enough. Okay, this is enough. THT, 2 raised to the power 3 is 8, 1 2 3 4 5 6 7, and one more is left. H T T. Okay, so these are all the outcomes which are probable. So you need to understand that each and every time, each and every time we will have a situation over here, it would be to the power of 2, 2 raised to the power of n. If there is a single flip, 2 raised to the power 1, we will have two probable outcomes. If we will have 2, it's going to be 2 square, which is equal to 4. And if there is going to be a 3, we would be sitting at 2 cube, which is equal to 2 raised to the power 3, which is equal to 8. Okay, so these are the possibilities. These are the possibilities which I would get, and possibilities in the form of sample spaces. Okay, so moving ahead, when an unbiased coin is tossed once, the possible outcomes are 2 raised to the power n, which is equal to 2. The sample space would be heads or tails. Similarly, um, two unbiased coins are tossed simultaneously. So it will be head head, head tail, tail tail, and tail head. And when three unbiased coins are tossed, I have given you the sample space on the previous page. The sample space would have 8 elements in it, okay, or 8 entries into it. Moving on, the question says a coin is tossed 5 times. Find the total number of probable outcomes. So it is asking us to create the sample space. As we already know the formula, it would be 2 raised to the power n, and here n would be equal to 5. So 2 raised to the power 5 would be 2 to the 4, 4 to the 8, 8 to the 16, 16 to the 32. So 32 would be my final answer. Okay, total number of probable outcomes would be 32. All right, moving ahead. When two unbiased coins are tossed up simultaneously, find the probability of getting no tails, at least one tail, and at least, or there's nothing, just one head. Okay, we have two unbiased coins. I'll quickly draw up the sample space: head head, tail tail, head tail, and tail head. Okay, talking about the first question, no tails. Okay, no tails is available only in the first option. So my answer would be, for the first one, would be 1 out of 4. Secondly, talking about at least one tail. So there is one tail over here, there is a second tail over here, and there is a third tail over here. So we have 3 out of Four possibilities, because the head and head does not have any tail, so we will not take that into consideration. Talking about point number 3, which has one head. Okay, it says one head. So this is not going to work, this is not going to work, this is going to work, and this is going to work. So the possibility of the third one is 2 by 4. Okay, so I have given you the output of all the three. If you can create your sample space, then the question becomes very easy. Okay, the question becomes very easy. I would like to explain you what is going on in the mind when we are talking about option number 2 over here. It says at least one tail. Okay, it says at least one tail. When I talk about one tail, what we mean here is that if there are zero tails, it's not going to be favorable for me. And no matter how many tails come beyond the first tail, I would be accepting all of them. Okay, so you start with the first tail, and I'm ready to accept as many numbers of tails as there are. But I would not accept the situation where I don't get a tail. Okay, I would not accept the situation where I don't get a tail. So I hope I've made myself very, very crystal clear. Do drop in some comments if you have any issues. Moving on. A coin is tossed 6 times. What is the probability of getting at least two heads? Okay, a coin is tossed 6 times. What is the probability of getting at least two heads? When I talk about getting at least two heads, this is the sample space which I have available for me: 1, 2, 3, 4, 5, and 6. Okay, so I would be dealing with it in a reverse engineering manner. Okay, what is the probability of getting at least two heads? Number one, you need at least two heads, right? So in the first situation, I'll talk about the unfavorable cases. Unfavorable cases. Unfavorable case number 1 says no head. Unfavorable case number 2 says only one head. Okay. Okay. What does the favorable case say? Two or more heads. Okay. But my focus is only going to be unfavorable cases over here. No head or only one head. Okay. So as I have made myself clear that I'll be following this approach, I am going to rub off this approach on the right hand side. Okay. I just need a little more space to help you understand what we are going to do. This is the first one, second one, third one, fourth one, fifth one, and sixth one. Let's assume that there are no heads at all. In that case, all my 6 coins would be reading tails. And how many times would that be possible that all the coins together, or this, when I'm tossing the coin 6 times, all the tails would come? That would be only one time. Okay. In my second occasion, when I again have 6 tosses available, see, you can toss 6 coins once, or you can toss one coin 6 times. The output is going to be the same, the sample space is going to be the same, the case is also going to be the same. Okay, so if I'm using it like interchangeably, need not worry about it. We are only getting this above output only once. Okay, so the frequency which we are talking about, or the probability we are talking about, is only once. Secondly, we are talking about only one head. Okay, so in the first flip we got a head, and in all the other flips we got a tail. So this is one favorable case. In the second flip we got the head, and rest all the time we got tails. In the third flip, we got heads, and rest all the time we got tails. Similarly, fourth flip head, rest every time tails. Fifth flip head, rest every time tails. And sixth flip head, and rest all the time tails. Okay, so there are going to be six such possibilities when you would be getting head at different places, and that would be only one head in the entire try. Okay, what is the total number of tries that we're talking about? What is the total number of tries that we're talking about? In case of coins, we've already established this fact that 2 raised to the power n is my final output. So final output, or the total number of instances, the total number of instances when the sample space would be created. Okay, so 2 raised to the power 6 would be the answer. When I talk about 2 raised to the power 6, it would be 2 raised to the power 6, it would be 64. So 64 is my entire sample space. Out of that, I have no head situation once, and only one head situation 6 times. So the value of 1 plus 6 is equal to 7, and my final answer would be 7 upon 64. My final answer would be 7 upon 64. But is that a favorable case that we're talking about? No, that is not a favorable case we're talking about. We are talking about the unfavorable case. And just now, like 15 minutes back, I have told you that favorable plus unfavorable together make 1. So the answer of my favorable probability would be equal to 1 minus 7 upon 64, which is equal to 57 upon 64. And this is my final answer. This is the most detailed format of teaching, and I've taught you each and every point over here. So I want you to pause the video, let it sink in, just understand what we've just gone through, and try to copy it. Okay, try to copy it in your exams. Need not draw this entire thing. Just remember, heads are supposed to come 6 times. It's supposed to come because we have 6 coins, or we are crossing the coin 6 times. Tails are going to come only once when all of them wish to come together at the same time. So only once that's gonna happen. So 6 plus 1 is 7. 7 upon 64. Pen and paper is not needed, but conceptually, I had to use it for you. Okay, moving ahead. Now we are sitting at dice. Okay, now we are sitting at dice. In a die, sample space is equal to this. Okay, sample space is 1 2 3 4 5 6 because they are nothing but the all the faces of the die. They are nothing but all the faces of the die. Similarly, if one die is rolled, then 6 raised to the power 1 would be the probable outcomes. 6 square to be the number of times, like if the die is rolled twice, and 6 raised to the power 3 if the die is rolled 3 times. Okay, whatever comes at the top, whatever comes at the top is the number which we are looking for. Okay, these are the other faces on the left hand side or on the right hand side. A dice is thrown. Find the probability. First of all, the sample space when one dice is thrown is 1 2 3 4 5 and 6. Okay, this is the sample space. Now, getting an even number, the probability of getting an even number. First of all, I would have the sample space. The size of the sample space is 6. So 6 would be in the denominator. What about the numerator? Even number. There are 3 even numbers, 2, 4 and 6. So my answer would be 3 by 6 or 1 by 2. Okay, there is a half probability of receiving even numbers when you throw one dice. Talking about getting a number which is greater than 4, so the probability of greater than 4 would be equal to 1 and 2. Okay, there are two instances out of 6 total instances, so my answer would be 1 upon 3. Getting a multiple of 2. Okay, for getting a multiple of 2, the options are 2, 4 and 6. So the probability of divisible by 2, okay, I have used the wrong sign. Okay, this is divisible by 2, would be equal to 3 upon 6, which is equal to 1 upon 3. Okay, which is equal to 1 upon 3. And I hope you've understood it. I hope you've understood it pretty well. Okay, moving further. We are now going to talk about all the possible cases when two dice are thrown simultaneously. This is also possible. This sample space is also going to be valid when one dice is thrown twice. Okay, when one dice is thrown twice. So 6 raised to the power n and 6 square, which is 36. Similarly, it could be 6 cube as well if there were 3 dice available, or one dice was thrown thrice. Okay, so 6 cube is nothing but 216, and this is the sample space. If you can recall it, if you can remember it, it will be good. If you can't, it's okay. Okay, it will be logical enough for you to remember it. It's not very difficult. Okay, it's nothing but a couple of numbers together. Okay, there is a limit to the numbers, that the first number cannot be greater than 6. It has to lie between 1 and 6. Similarly, the second number also has to be equal to 1, or has to be equal to 1, and between, it's supposed to be between 1 and 6. As simple as that. Okay, all the probable numbers which can appear on the die would be a part of the sample space that we have over here. Okay, two dice are thrown simultaneously. Find the probability of the sum being 10. Okay, the probability of sum being 10. First of all, I would find out the size of the sample space. The sample space is going to be 6 square, okay, which is equal to 36. So all my denominators are going to be 36. Okay, so for the first option, the denominator is 36. Similarly, for the second one also, I'll code the denominator as 36. For the third one, the denominator again is 36. And for the fourth one as well, the denominator is 36. Okay, this is established. Now I need to find out my sum as 10. There would be how many options? Let me check. 5 and 5 once, 4 6 6 4. Okay, I don't think there is a third option. I'll check it from my sample space. 5 and 5, 6 and 4, 4 and 6. Okay, nothing would give me the sum as 10. So this is 3 upon 36 or 1 upon 12. Simple, solved. Second, doublets. Okay, doublets means that both the numbers are which are occurring are the same. So doublets would be 1 1, 2 2, 3 3, 4 4, 5 5 and 6 6. So there are 6 occurrences of doublets, and 6 upon 36 is nothing but 1 by 6. Simple, simple. Moving on. A multiple of 2 on one dice, and is the important catchword over here, and multiple of 3 on the other die. Okay, when we are talking about the multiple of 3 on the other die, the number of multiples of 2 is going to be larger as compared to the number of multiples of 3. Okay, the number of multiples of 2 is going to be larger as compared to the number of multiples of 3. So it would be better if I choose the multiples of 3, if I check the multiples of 3. So this is the row, this is the row where there are multiples of 3, and this is the row where there are multiples of 3. This entire column and this entire column. Now I need to check the multiples of 2 on the first die. The multiples of 2 on the first die are 1, 2 and 3. Similarly, the multiples of 3, like the multiples of 2 on the second die are 1, 2 and 3. So here I again have 6 outcomes out of 36 outcomes which are in my favor, and I would write the answer as 1 by 6. Simple. More than 10 as a sum of both the dices. This is the next problem. See, I get the sum of 10. I'll just change the color of the pen. I'm getting the sum as 10 straight away on this die, 5 comma 5. But point over here, pointing to over here, 5 comma 6, 6 comma 5, and 6 comma 6. Okay, so these are the 3 points where the sum is 11 and 12. Okay, we don't have to consider the sum as 10 because it has not said the sum can be equal to 10. It says only greater than 10, which is equal to 11 or maybe 12. Okay, so we have three options over here: 6 5, 5 6, and 6 6. So the option is 3 by 6, 3 by 36, which is again equal to 1 by 12. Okay, so you need to have the sample space in your mind whenever you're solving such a problem. Okay, so moving ahead, a die is rolled 3 times. Find the total number of possible outcomes which can come. 6 raised to the power n is the answer, and 6 raised to the power 3 has been asked. The cube of 6 is nothing but 216, which is my final answer. Okay, moving ahead. Now we've reached a very, very important juncture, the most important of all the questions which ever come for probability. Okay, they are cards. Okay, a deck of cards. A set of cards is basically called a deck of cards, and there we have the option of total number of cards being 52. Okay, there are four kinds of cards. I'll just tell you how it basically works. The entire deck has 52 cards. Okay, I'm sorry, the entire deck has 52 cards. All right, and from those 52 cards, the first set is 26 and the second set is also 26. The first 26 being red and the second 26 being black. Okay, red, red. Okay, now remember this: hearts are red, the heart is red. Okay, the heart pumps blood, blood is red, so heart is red. Secondly, diamonds, diamonds. Okay, diamonds are very close to the heart, so they are also red. So heart is red, diamond is red. Okay, simple. Then there are two more options, which are spades and clubs, which are black in color. Okay, now each of these decks is divided into 13 each. Okay, there are 13 hearts, 13 diamonds, 13 spades, and 13 clubs. Okay, so once this equation is through, you'll be able to, like, it'll give you a better idea of how to solve questions once this entire diagram and this map is clear. Okay, in each and every shape, okay, I'm calling these shapes, in each and every shape the constituents are the same. Okay, the constituents are the same. There would be a king, there would be a club. This is nothing but houses. Okay, in each and every house, in each and every house, the house of hearts, the house of diamonds, the house of clubs, and the house of spades. In the house of hearts there is one queen, one king, one jack, one ace. Okay, out of these, the first three, the king, queen, and jack, these are called face cards. Why are they called face cards? Because they literally have the faces, they have diagrams over them. Okay, they have pictures, they have pictures of a queen, of a king, and of a jack. Okay, on the next slide itself I'll be showing you what sort of a, like, how the cards look. I'll be showing you that. So king, queen, and jack, three, these are the face cards. Then there is an ace, which is the first ace, and then there are number cards. The number cards start from 2 and go up till 10. Okay, the number cards are 9 in number. Remember that the number cards are 9 in number, and this is the same across all the houses, and we are talking about one house over here right now. Okay, 52 playing cards, there are four suites. Okay, sorry, there are four suits, there are four suits. Okay, when I say house, I also mean suit by it. Okay, house or suit. I'm improving day in and day out just for you. Okay, four suits: spade, heart, club, and diamond. Okay, there are 13 cards in each suite, in each suit: four aces, four kings, four queens, and four jacks. This is across all suits. Okay, this is across, valid across all suits. Okay, I'll be moving ahead. So this is the clearest picture which you'll ever get. Okay, this is the ace. Okay, this is the ace, and this heart, this is called, this shape is called spade. The ace would also have the similar shape as the suit in which it is. Okay, it would have the similar shape. See, this is the shape. This is the shape of a spade. Okay, this is the shape of a spade, and it would have the same shape with it. Talking about the face card, this is the face card 1, this is the face card 2, and this is the face card 3. See, this is a king and this is jack. The king would be looking straight, and the jack would be looking, you would see only half the face of a jack. Okay, you would see the entire face of the queen as well as the king. Okay, you would see the entire face of the queen as well as the king. I'll just show it to you. Just give me a moment. Okay, the ace that we've talked about over here, we have the ace over here, then we have the jacks over here, we have the queen over here, and we have the king over here. Okay, I've already talked about the face. The face, both the eyes are visible, both the eyes are visible, and only one eye is visible because it's like one-sided face. And here also both the eyes are visible. Then we have the number cards. The number cards being 2, 3, 4, 5, 6, 7, and then 8, 9, and 10. Okay, simple. Then we have the possibility of there being an ace. So basically constitutes this basically constitutes one suit. Okay, this constitutes one suit. This entire thing is one suit. And what is it the suit of? It is the suit of spades. Okay, simple. Yep, moving ahead. So we have the sample space to be 52. The sample space is equal to 52. There would hardly be a question when they tell you that there are more than one decks. Okay, there would only be one deck, and we'll be shuffling that, and we'll be using the sample spaces from that. So one deck would have the entire sample space of 52 cards. Okay, what is the probability of drawing two spades from a well shuffled deck? Okay, first of all, if I draw one spade, first of all, let me be clear, what is the number of spades? What is the number of spades? The number of spades is 13. Okay, so once I draw 13 out of 52, and then I have to again draw. Okay, now I have to again draw. If I have to again draw, then the number of spades is going to go down. It's going to be 12 spades. Out of 12 spades I would be drawing, and there would be 51 total number of cards left. Okay, so 13 by 52 multiplied by 12 by 51, and this would give me my answer as 3 fours are 12, 3 17s are 13 ones are 13 fours are. The 4 and 4 would go away. So 1 by 17 is the probability of drawing two spades of a well shuffled deck of 52 cards. Got it? Got it? Moving on to the next question. One card is randomly drawn from a pack of 52 cards. What is the probability that the drawn card is a face card? Okay, we're talking about the face card. We have three face cards in each suite, and there are four suits. So we have 12 face cards. 12 face cards out of a possibility of 52 sample space, which is uh four, like, wait a second, 4 ones are 4, 4 threes are 12, and 4 threes are 12. So 3 upon 13 is my probability. 3 upon 13 is my probability because my sample space remains the same, which is equal to 52. And then talking about face cards, we have three face cards in one suit, and we have four suits. So we have a total of 12 face cards. Okay, the ace is not considered a face card. Remember it. Okay. Ace does not have a face on it, so ace is not considered a face card. Secondly, now this question, one card is drawn randomly from a pack of 52 cards. The probability of the card drawn being a red and a queen, 10 of a black suit, an ace, and either red or king. Okay. So the first one is a red and a queen. The probability of drawing red, the probability of having red and a queen. Okay. So there are two red queens out of 52 total cards. So the probability would be 2 upon 52 or 2 upon 52 or 1 by 26. So only one card is being drawn. And when I talk about queens, there are only be two possibilities. One that of diamonds and second of hearts. Okay. Diamonds and hearts, only two red queens. 10 of a black suit. In a black suit, there are only two tens. Okay. One of the spades and the other one of, just a second, spades and clubs. I always tend to forget the names. Spades and clubs. Okay. There is only going to be one 10 over here and another 10 over here. So 2 out of 52 or 1 upon 26. So this is also correct. An ace. We have four aces. Okay. One in every suit. So for four aces, we have 52 over here and 1 upon 13 is my answer over here. Either red or king. Okay. So we have to add the probabilities. If you're talking about either red, it means that there are 26 cards which are red and 52 is the total number. Add it with that of a king. There are four kings out of the 52 cards. Okay. So we have to add the probabilities, and after the adding the probabilities, we get the answer as 30 upon 52, and the answer is 15 upon 26. Okay. After solving, see, I'm not talking a lot about I'm not talking about a lot about the sample space and everything, because it is pretty evident that the sample space is not going to go beyond 52 cards. Okay. So you might be feeling that the speed is a little quick, but trust me, this is the speed which you must have in the examination as well. Now we're talking about a box containing numbered cards from 6 to 50, and one card is drawn from random from the box. What is the probability of it being a perfect square? First of all, I'll talk about my sample space. My sample space being 50 minus 6 plus 1, because I have to include, maybe I have to include the 6 in it as well. So my sample space is 45 cards. Okay, I have a total of 45 cards that will stay in the denominator forever. We're talking about finding the probability of there being a perfect square. From 6 to 9, 6 to 50, there are these many perfect squares. There's 9, 16, 25, 36, and 49. Okay, 3 square, 4 square, 5 square, 6 square, and 7 square. So we have the possibility 1, 2, 3, 4, and 5. So we have 5 of them. We have 5 of them in the probability, and there being a perfect square out of the entire sample set. The entire sample set is of 45. So my answer is nothing but 1 upon 9. Okay. So this brings us to the core, to the end of the core of probability. Now there are extensions of probability which would be going towards permutations, combinations, and other miscellaneous questions which have been asked through the times. But this is the most standard core of probability. The core areas you've talked about, I've told you about the cards, I've told you about the dice, I've told you about the coin. Okay. So these are the standard protocols which you need to follow whenever you study probability. Now, in the next round, we'll be taking up permutations, combinations, and other miscellaneous options. Now we are at the topic of permutations. Permutations is used in probability because permutations help us to find out the number of ways in which an arrangement is possible. The number of ways in which an arrangement is possible, that is found with the help of permutations. What do we actually do in it? We have the formula of P of permutations as P n comma r is equal to n factorial whole upon n minus r factorial. What does the word factorial mean? Factorial means that n has to be multiplied with numbers less than itself by minus 1 till the time it reaches 1. So n factorial is nothing but n multiplied by n minus 1 multiplied by n minus 2 multiplied by n minus 3 and so on till 1. Okay, please consider them to have brackets because if you'll see bod mass, then you'll get tricked into solving it in the wrong way. So n multiplied by n minus 1, you have to first solve n minus 1 and then multiply it by n. Let's assume I'm talking about 5 factorial. So 5 factorial is nothing but 5 into 4 into 3 into 2 into 1. Okay, so this is the definition of factorials. I hope you are able to understand what factorials mean now. Now I'll talk about 4 factorial in a very similar manner. Okay, 4 factorial means 4 into 3 into 2 into 1. If somebody asks me that I have to write the the answer of 5 factorial in terms of 4 factorial, so what can I do? I can easily see that 4 factorial is already present in 5 factorial. The only difference is that 5 factorial has an additional 5. Okay, it has an additional 5 because that is n. So 5 multiplied by 4 factorial can also be called 5 factorial. Similarly, if I'm supposed to write 5 factorial in terms of 2 factorial, what do I do about it? Or rather, let's say 3 factorial. So I'll have to write it in this manner: 5 into 4 into 3 factorial. What does 3 factorial actually stand for? 3 factorial stands for 3 into 2 into 1. Okay, 3 factorial stands for 3 into 2 into 1. So I already have it in place, and 3 into 2 into 1 is already present in the term of 5 factorial. Okay, so I hope you understand what permutations are used for. These are going to give us just the arrangements, all the possible ways in which a favorable arrangement is possible for us. What does n and r stand? What do n and r stand for? N stands for the total set. Total set means the total number of things that are supposed to be arranged in a particular manner. What does r stand for? R stands for the number of favorable items in the set. The number of favorable items in the set which need to be arranged. So total set and favorable set, or total set and favorable items. So I hope you've understood the theory part of it. Let me take you to the one question which has been asked by SSC. In that question, you'll be able to understand how permutations are used. Okay, suppose you have 5 different books on a shelf and you want to arrange 3 of them in a specific order. Then the number of permutations can be calculated as what? I have 5 different books available with me. I need to arrange 3 of them. So I can easily say this is 5 P 5 comma 3. 5 is the total number of books. 5 is the total number of books, and 3 are the favorable number of books. So P 5 comma 3. I have P 5 comma 3. I'll quickly solve it by putting 5 factorial over here and 5 minus 3 whole factorial over here, coming down to a point where 5 factorial is 5 into 4 into 3 into 2 into 1 whole upon 5 minus 3 factorial, which is 2 factorial. 2 into 1. 2 into 1 gets cancelled. 5 4s are 20. 23 is a 60. So 60 is my answer. Okay. The number of permutations can be calculated as 60. I hope you are able to understand. Now we'll go to a point which is just a tad bit more difficult as compared to what we've studied. This is simple permutation. Now we will be using permutations and combinations in probability. So this is the first question of it. Now, the question says a person can hit a target 5 times out of 8 shots. If he fires 10 shots, what is the probability that he will hit the target twice? He will hit the target twice. Okay. Here we'll have to apply combinations because we are selecting things. We are selecting things. What happens when we select things? What happens when we select things? So what happens when we are selecting things? We use the formula of C, or which is called the formula of combinations. It is represented as NCR, and NCR stands for n factorial divided by r factorial multiplied by n minus r. Okay. So whenever we get a choice of selecting something out of a permutation, that is when combinations are used. Okay, that is when combinations are used. So here I can see the probability. The probability of hitting the shot is 5 times out of 8 times. The probability of missing the shot, the probability of missing the shot is 3 times out of 8 times. Okay. Now the shot is being shot 10 times. Okay. So that means 10 is the total set. 10 is the total set. Out of those total sets, how many favorable outcomes do we require? We want the target to be hit twice. So what do? I write 10C2. Now there has to be a multiplication sign because we are going further in the equation. What do we talk about here? 10 shots are being fired and the probability of hitting twice, of hitting the target twice is needed. So the probability of hitting is 5 by 8. The probability of hitting is 5 by 8 and this probability should sustain 2 times. What about the probability of missing? The probability of missing is 3 by 8 times, and out of a total out of a total of 10 shots, 2 of them have to be favorable and 8 of them can be unfavorable. It won't be a problem if these shots are missed. Okay, 3 by 8 shots should be missed, and out of a total of 10 they can be missed 8 times, and out of a probability of 5 by 8 they are supposed to be done 2 times. Okay, they are supposed to be positive 2 times. So when I solve this equation, I see that 8 by 10 is common to all the equations. Okay, 8 by 10 or 8 raised to the power 10 is common in every equation. What about 5 square? 5 square stands for 25. What about 3 raised to the power 8? 3 raised to the power 8 is also common to all the equations. 3 raised to the power 8 is also common to all the equations, so I won't solve it. What about solving 10C2? 10C2 can be solved in a manner like 10 into 9 into 8 factorial. Okay. And 10 minus 2 factorial is nothing but 8 factorial. What about 2 factorial? 2 factorial is nothing but 2 into 1. I'm not writing 1 over here. The 8 factorial gets cancelled. 2 ones are 2, 2 fives are 10, right? So I have 5 5 into 125 into 9, which comes out as 1125 multiplied by 3 raised to the power 8 whole upon 8 raised to the power 10. So D option is my correct option. Okay, D option is my correct option. Moving to the next question. So we are now going to talk about combinations. Okay, we're going to talk about combinations in probability. What does combination really help us with, and what is the basis in which combination are used? Combinations are used for selecting certain arrangements. In permutations, there were arrangements that were supposed to be made. In combinations, there would be selecting. Okay, there would be selection ways. So in how many ways? In how many ways a favorable combination, a favorable combination is selected. For that, we have NCR, that is the formula, which is also called C n comma R, and the final point comes out like n factorial whole upon R factorial multiplied by n minus R factorial. So n factorial whole upon R factorial in the bracket n minus R factorial. This is it. This is the point. So I'll be taking you through the questions now. Let us consider the same set of 5 books, but this time you want to select 2 books without caring about the order. No matter the 2 books come together or they don't come together. So we need to find out the number of calculation, not the number of combinations can be calculated by what method. Here we would use NCR or the formula of combinations, which is nothing but 5C2. 5 is the total point and 2 is the favorable point. Okay. So 5C2 stands for 5 factorial whole upon 2 factorial multiplied by 5 minus 2 factorial. 5 factorial in terms of 2 factorial will be writing. The reason is that because instead of calculating 2 factorial, then cutting off the specific terms which are there in 5 factorial, it is better to represent it in this way: 5 into 4 into 3 into 2 factorial. Okay, easily it's going to get cut. This is again 2 factorial and this is going to be 3 factorial. 3 factorial can be cut off right away because 3 into 2 factorial is equal to 3 factorial. 2 factorial then can be expanded like 5 into 4 whole upon 2 into 1. So 2 ones are 2 twos are. So the total number of combinations that can be made are 10 combos. Okay, 10 combos can be made. The answers are considerably short because the concepts are considerably short. Okay, so I hope you understood. Let's move on. A coin is tossed 6 times. What is the probability of getting at least 3 heads? Okay, let's assume the coin was tossed 6 times. The first time, the second time, the third time, the fourth time, the fifth time, and the sixth time. The probability of getting at least 3 heads. That means the situation has to be heads, heads, heads. This is the situation, and then any outcome is okay. If we get heads again, it's fine. If we get heads one more time, it's fine. And if we again get heads, it's completely fine. Okay. But if we get tails over here, tails over here, and tails over here, that is also fine. So all the combinations in the last three are completely fine. Only the first three or any three of them should be heads. Okay. At least 3 heads. So what we'll do, we'll try to find out the probability of getting 3 heads first, then the probability of getting 4 heads because that is also favorable, the probability of getting 5 heads, and the probability of getting 6 heads. Okay, we have all the probabilities and all the possibilities that we are going to check. So we'll be using this technique that the coin is not biased. Okay, the coin is not biased. When the coin is not biased, what does it help us with? The probability of heads coming in a single toss is going to be one of the two. It means out of the probability of either heads coming or tails coming, if I'm only seeking the probability of heads coming, that is 1 by 2. Why do I say 2? 2 means either heads or tails. 1 means only heads. Okay. So the probability of tails coming is also equal to 1 by 2. Okay. It's an equally probable situation. So for 3 heads, out of the 6 tosses, I will be choosing 3 tosses. And in those 3 tosses, I would be expecting the probability of heads coming thrice and the probability of tails also coming thrice. Okay. This is the probability of heads on the left hand side, and this is the probability of tails on the right hand side. Okay. I hope you are able to understand. Similarly, when 4 situations are cut up, the option comes up as 6C4. Okay, the options come up as 6C4. Again, It is half raised to the power 4, means the probability of 4 heads coming. And in the rest of the two remaining tail points, that is going to be 1 raised to the power 2. Again, 6c5 multiplied by half in raised to the power 5 and 1 by 2 raised to the power 1. Similarly, for 6 heads coming, it is going to be 6c6 multiplied by 1 by 2 raised to the power 6 multiplied by 1 by 2 raised to the power 0. If I add up all the powers of these consecutive brackets, I can see that all the powers are going to add up to 6. That means the number of tosses are 6. I'll quickly have to add all of them up to find out the final probability. Let me first solve the first equation. 6c3 is nothing but 6 into 5 into 4. Whole upon 3 factorial would get cancelled. 6 minus 3 is 3 factorial. 3 into 2 multiplied by 1 by 2 raised to the power 6. Similarly, 6c4 is nothing but 6 into 5. The 4 would get cancelled off. Then 6 minus 4 is 2. 2 into 1. Again, it would be multiplied by 1 by 2 raised to the power of 6. Similarly, 6c5 stands for 6 factorial, which would 5 factorial would get cancelled, and 6 minus 5 is 1. So 6 upon 1 multiplied by 1 by 2 whole raised to the power 6, because 5 plus 1 is 6. Then 6c6 is nothing but 1 multiplied by half raised to the power 6. Okay, so I hope these situations are completely in place. So 1 by 2 raised to the power 6 comes common, and I'm adding all of them up. Okay, I'll quickly solve whatever I can before it even comes to my summation point. Okay, this is the summation point where I have put equals to. 3 2s are 6, 6 is gone. 2 3s are 6, 3 is here. Okay, 5 4s are 20, 3 5s are 15, plus 6 plus 1. Okay, this gives me how much? Yeah, this gives me 35, 41, 42. This gives me 42 divided by 2 raised to the power 6. The value of 2 raised to the power 6 is 64. So 42 upon 64, 2 21s are 2 32s are. So 31 upon, 21 upon 32 is my final answer. Okay, I hope you have understood whatever I have talked about here. Moving on. Now, in how many ways the letters of the word coconut can be arranged? I'll quickly count the number of letters: 1, 2, 3, 4, 5, 6, and 7. Okay, so here, from in 7 places, I have to select, in 7 places, I have to select 7 letters, right? In 7 places, I have to select 7 letters. So that means 7 factorial is the output. But I have to take care of the things or the letters which are repeating. Here, 2 letters are repeating. 2 is coming twice, and O is also coming twice. So I'll have to divide that by 2 factorial. I'll have to divide that by 2 factorial. Yeah. So 7 factorial divided by 2 factorial and 2 factorial. Why did 2 factorial come twice? The reason is that there was C over here and there was O over here. 7 factorial stands for 7 into 6 into 5 into 4 into 3 into 2. 2 factorial stands for 2 into 1 and 2 into 1. So 2 2s are 4. This is the only thing which will get cancelled out. 5 2s are 10, 10 3s are 30, and 30 into 42. 3 2s are 6, 3 4s are 12. 1260 is my answer. Okay. These are the ways in which the letters coconut can be arranged. Okay, 1, 2, 6, and 0. All right, moving on. Find the number of such words that words, not this is not words, words that can be formed from the letters used in the word reply. Okay, these are all distinct words. REPLY. Now, all the words which end with Y. So there are four spaces, and the last letter has been fixed as Y. This means in four spaces, one, two, three, and four, any of the four words can come. That means the answer is going to be 4 factorial. Okay, the answer is going to be 4 factorial. What is 4 factorial? 4 into 3 into 2, 24 is the answer. Similarly, anything which starts with R. So the first one is R, and 1, 2, 3, and 4. These are 1, 2, 3, and 4. Anything can come in that place. That means again 4 factorial, and the value of 4 factorial is nothing but 24. Similarly, choose the letter L is always in the middle. If L is always in the middle, the first two are going to remain as it is, and the next two are going to catch up new areas. Okay, so 1, 2, 3, and 4, four blanks are supposed to be filled. So 4 factorial would be the number of ways in which they can be filled, 24. Then a word which starts with R and ends in Y. This means R, 1, 2, 3, and Y as the last one. So I have 1, 2, and 3 spaces available. If I have 3 spaces available, 3 factorial would be my answer. 3 into 2 into 1, this would give my answer to be 6. Okay, moving on. In how many different ways can the letters of the word candidate be arranged in such a way that the vowels are always coming together? So I have the word candidate, CANDIDATE. In candidate, I have 1, 2, 3, 4, 5, 6, 7, 8, and 9 letters. So we have the word candidate with us, and the length of the entire word is 9 letters. So the vowels should come together. We'll separate the vowels out of it, the vowels, basically vowels out of it. So A, I, A, E. So A, I, A, E, these are four options. So out of four options, this makes it 4 factorial. Now, two of them are same, like A and A are same. So 2 factorial. This would be multiplied by, yeah. So this entire situation would be multiplied by the number of characters which are left behind plus 1. Why would I do plus 1 to that? Because I'm considering that all the vowels together are one entity. So we have 1, 2, 3, 4, 5, and plus 1, that is the vowels, which is one entity. So 6 factorial, 5 plus 1, 6 factorial upon the number of repetitions. In terms of repetitions, D is being repeated. Okay, D is being repeated. So another 2 factorial would come into the way. 6 factorial is 6 into 5 into 4 into 3 into 2 factorial multiplied by 4 into 3 into 2 factorial whole upon 2 factorial multiplied by 2 factorial. 2 factorial gets cancelled all the way. I have 6 fours are 24, 24 fours are 96, 96 multiplied by 9. No, I'll do it in a better way. 5 6 are 30, we have 30, 4 threes are 12, we have 12 here, and we have another 12 here. 12 into 12 is 144, 144 into 30 is my answer. 3 fours are 12, 3 fours are 12, 13, 3 ones are 3, 4. So 4320 is my answer. Right? Moving to the next question. Yeah. So talking about in how many ways can three artists, two doctors, and four lawyers be seated in a row in a conference hall so that all persons of the same profession can sit together? Okay. This means we have three professions. The first one being artists, the second one being doctors, and the third one being lawyers. So for these three professions, the first entry into the game would be 3 factorial. Okay, because there would be 3 factorial ways in which these people can sit. Okay, all artists together, all doctors together, all lawyers together, or first artists, then doctor, then lawyers, then doctors, or first doctors, then artists and lawyers. So 3 factorial would come for that. Then talking about artists. Inside artists, there are 3 people already. There are 3 people already. So these 3 people would have an internal rotation. So that internal rotation would call for another 3 factorial. For the 2 doctors, they would have another internal rotation calling for 2 factorial. And for the 4 lawyers, there would be an internal rotation of 4 factorial, which will create a rotation between them. So my answer would be 3 factorial into 3 factorial into 2 factorial into 4 factorial. This would give me 3 twos are 6, then again 3 twos are 6, 2 ones are 2, and 6 fours are 24. So what do I have here? I have here 36 into 48, or this is nothing but the cube of 12. Why? This is 12 into 12 into 3 into 4, that is again 12. So the cube of 12 is 1728, which is my final answer. Okay, good enough. Let's move on. 4 boys and 2 girls sit in a row. If 2 girls always sit together, find all the possible ways. Talking about the 2 girls sitting together, the ways in which they can sit together are going to be 2 factorial. 2 factorial means 2 ways. Let's say this is A1 is a girl and A2 is also a girl. So the 2 ways in which they can sit is A1 and A2 here. And the second way in which they can sit is A2 and A1. Okay. So this is the only way possible that they can sit together. Yeah. Further, there are 2 boys. Sorry. Further, there are 4 boys. There are 4 boys plus 1 set of girls. For those one set of girls, I've already said 2 factorial is going to be my output. This would be multiplied by 4 plus 1, which is 5 factorial, right? The value of 4 factorial is 24. The value of 5 factorial is going to be 120. 120 into 2, 240. So there are 240 possible ways in which these set of girls and 4 boys can sit together. Good enough? Easy enough? Let's move on. How many different teams of 6 players can be formed from 5 males and 5 female players? Okay. I need to pick 6 players. Simple combination formula. Okay. 10C6. 10C6. Out of a team of 10 people, I need to have a couple of, I need to have a group of 6 players. So 10C6 stands for 10 factorial whole upon 6 factorial multiplied by 10 minus 6. That means 4 factorial. This would go to 10, 9, 8, 7, 6 factorial whole upon 6 factorial multiplied by 4 factorial. The 6 factorial gets cancelled with 6 factorial. 4 factorial when expanded forms 4 into 3 into 2, right? 4 2 is a 8 is gone, 3 3 is a 9 is gone, right? So 7 3 is a 21, 2 1 0 is my answer. Okay, 210 is my answer. I hope you're able to get it. Simple enough. Let's move on. If two particular boys are to be selected always, then in how many ways can 6 boys be chosen from a total of 11 boys? Okay, this question is pretty interesting. So, 2 boys are already selected, right? 2 boys are already selected. Another 4 boys need to be selected. These four boys would be selected from a lot of how many more boys? Nine boys. So these four boys and two boys would make up for the six chosen ones. This would make the six chosen ones. So I need to simply follow 9C4 because of the nine boys who are left out of 11 boys. From them would be picked four boys. Okay, so 9C4. 9C4 stands for 9 factorial. I'll quickly write it down. 9 into 8 into 7 into 6 into 5 whole upon 4 factorial multiplied by 9 minus 4 factorial, which is 9 minus 4 whole factorial, which is 5 factorial. So the 5 factorial thing gets cancelled out. Now 4 factorial would be expanded. 4 into 3 into 2 into 1. Okay. Uh, 4 2s are 8. 8 is gone. Then 3, 3 is a 9 is gone. Okay. So 3 sevens are 21. 21 6 are 126. So my answer would be there are 126 ways so as to choose 6 boys out of 11 boys when two particular boys are already selected or they are always selected. Right? Good enough. I'll move on. So now we'll be focusing on the topic of colored balls. Okay. These are not what it was written, these are colored balls. Okay. So in this particular topic, what we're going to do is we'll be finding out probability of the favorable case. Okay, the probability of the favorable case. We have 6 white balls, 2 black balls and 3 red balls. Okay, if one ball is drawn at random, find the probability that the ball is not white. It means that the ball is colored. Okay, the ball is colored. There are two options, one is black and the other one is red. So there are two black balls and there are three red balls. So out of these 5 balls, I have to choose one. Okay. And what are the total number of balls? The total number of balls, including 6 plus 2 plus 3, makes them 11. So there are 11 balls. And out of the choice of 11 balls, I have to select one ball. So the answer is favorable upon total. Favorable upon total. The favorable case says 5C1 and the total case says 11C1. So 5C1 is nothing but 5 and 11C1 is nothing but 11. So 5 by 11 is my answer. Okay, 5 by 11 is my answer. I'll move on. There are 4 black balls, 3 red balls and 5 green balls in a box. If 2 balls are drawn out at random, find the probability of them being of the same color. This means that if there are 4 black balls, if there are 4 black balls, two of them should be picked and both of them should be black. Similarly, there are 3 red balls and if two of them are picked, then both of them should be red. And there are 5 green balls and if two of them are picked, they are supposed to be green. Also, out of a total of 4 plus 3, 7, 7 plus 5, 12, out of a 12 total, two balls need to be picked. Okay. So what would the answer look like? The answer would be 4C2 for black, 3C2 for red, 5C2 for green, and 12C2 for total. I'll quickly do 4C2. 4C2 stands for 4 into 3 into 2 into 1 whole upon 4 minus 2 is 2 factorial multiplied by 2 factorial. The 2 factorial gets cancelled with 2. This 2 gives me 1 and 2. The answer comes out to be 6. 3C2 stands for 3 factorial whole upon 3 minus 2 is 1 factorial and 2 factorial itself. This would give me 3 as my answer. Then talking about 5C2. 5C2 stands for 5 into 3 into 2, sorry, 5 into 4 into 3 into 2, whole upon 3 into 2 into 2. This 2 is 2 and 2 is gone. This 2 and 2 gives me 2. 2 and 4 gives me 2. The 3 and 3 gets cancelled out. 5 twos are 10. So what I get in the numerator is nothing but 6 plus 3 plus 10. Then talking about the total. Total is 12C2. 12C2 stands for 12 into 11 into 10 factorial whole upon 10 factorial multiplied by 2 factorial. 2 factorial is 2. This would give me 6. The 10 factorial get cancelled with 10 factorial. This now gives me 66. So 66 is my answer over here. Finally, my final answer would be 19 upon 66. Okay, 19 upon 66. This is my final answer. Moving on. A glass jar contains 6 white, 8 black, 4 red, and 3 blue balls. If a single marble is chosen at random from the jar, what is the probability that it is black or blue? If I check the probability of it being black, so out of 8C, I have to select 1. Then talking about blue, out of 3C, I have to select 1. These two probabilities would be added and they would be taken out from what? They would be taken out from 6 plus 8, 14. 14 plus 7 is 21. They would be taken out from 21C1. Okay, 14 plus 7, 21. Yep, that is correct. So 8C1 stands for 8 plus 3C1 stands for 3 upon 2C1. The 21C1 stands for 21. So my final answer would be 11 upon 21. You can see how quickly we are arriving at our solutions, right? So I'll move ahead. Two friends, now these are miscellaneous questions, okay? Two friends A and B are appearing for an interview. The probability of A being selected is 1 by 8. The probability of B being selected is 1 by 4. What is the probability that both of them will be selected? This is a favorable case. This is a favorable case. If both of them are supposed to be selected, the favorable cases would be multiplied with each other, right? A multiplied by B, the favorable case of A or the probability of A would be multiplied by the probability of B. This gives me 1 by 8 into 1 by 4, which is nothing but 1 by 32. Okay. The probability of both of them being selected is 1 by 32. Moving to the next question. Yeah. So the probability of the husband's selection is 1 by 7 and the probability of wife's selection is 1 by 5. What is the probability that only one of them will be selected? This means the husband is selected, the wife is not in the first case, and the wife is selected and husband is not selected in the first case. The probability of husband being selected is 1 by 7. The probability of the husband being rejected, okay, I'm putting a cross on it, is 6 upon 7. Okay, the probability of something happening plus the probability of something not happening is always equal to 1. Okay, this is equal to unity. So we have 1 by 7 and 6 by 7. Similarly, the probability of the wife to get selected is 1 by 5 and the probability of wife not being selected is equal to 4 by 5. What do I have to do now? I just have to put my values in this equation. My answer would be 1 by 7 multiplied by 4 by 5 plus 1 by 5 multiplied by 6 by 7. This would give me a denominator of 35 and a numerator of 4 plus 6, which is equal to 10. So 10 upon 35, 5 twos are 10, 5 sevens are 35. 2 by 7 is my answer. Okay, 2 by 7 is my answer. Good enough. I'll move on. A speaks the truth 5 out of 7 times and B speaks the truth 8 out of 9 times, what is the probability that they contradict each other in stating the same fact? This means that one of them is speaking the truth, one of them is lying. We have to form pairs of it. Okay? If A speaks the truth, he does it 5 by 7 times. If A speaks false or A speaks tells a lie, it is a 2 by 7 times. Similarly, if B speaks the truth, it is 8 by 9 times. If B tells a lie, it is 1 by 9 times. Good enough. Now I need to contradict both of them. So one of them has to tell the truth, the other one has to tell a lie. Okay? So I'll simply be cross multiplying things because my answer is nothing but A telling truth, B telling lies or B telling false, plus B telling truth and A telling false. These would be multiplied in the middle and added up. This gives me my answer as 5 by 7 multiplied by 1 by 9 plus 2 by 7 multiplied by 8 by 9. This would give me 5 by 63 plus 16 by 63. This would all come down to 21 by 63. 21 ones are 21 threes are. My final answer is nothing but 1 by 3. Okay? This is my final answer. Good enough? Let's move on. Find the probability that a number selected from the numbers between 1 to 25 is a prime number when each of the number is equally likely to be selected. Now, in probability, you will find all the questions where the possibility of selecting some number is equally likely always. Okay. So the last line doesn't hold a lot of sense. It really tells you that there is no biasness when we try to pick things out. Okay. Selected from the numbers to 1 to 25. From 1 to 25, I now need to recollect which one of them is prime and which one of them is not. The number which is prime, the number which is prime starts with 2, 2, 3, 5, 7, 11, 13, 17, 19, 23. Yeah, I'll check things in the middle. 4, no. 6, no. 8, 9, 10. Yeah, 12, 14, 15, 16, 18, 20, 21, 22, 23, yes. 24, no. 25, no. Okay, so these are the prime numbers. What is the total count of prime numbers? 1, 2, 3, 4, 5, 6, 7, 8, 9. I have a total of 9 prime numbers between 1 to 25, and the total set of numbers are 25. So the possibility or the probability of we picking a prime number is 9 upon 25. Got it? Good enough? Let's move on. A number is selected at random from 1 to 200. What is the possibility that it is a multiple of 6 or 9? Okay, we need to tell the possibility, the probability of it being a number of a multiple of 6 or 9. So if I need to find out all the multiples below 200 which are divisible by 9, I'll simply do 200 upon 9. Okay, whatever the quotient is, that is the total number of multiples which are below 200. 9 twos are 18 and 9 twos are 18. So there are 22 numbers which are below 200 which are divisible by 9. Further, I'll have to check the same of 9 of 6 of 6. So for 6 and 9, for 6 the possibility is going to be 6 threes are 18 and 6 threes are 18. These are the two questions which I'm talking about. Now, if I simply add up these two quotients, what I would get is I would get all the numbers which are divisible by 6, and I would get all the numbers which are divisible by 9. But there would be a double counting. What is that double counting? The LCM of 6 and 9 is 18. It would count the numbers lower than 200 which are divisible by 18 twice. once in the table of 6 and once in the table of 9. So to avoid the problem, what I should do is I should quickly check what are the numbers under 200, what is the total size of the numbers under 200, or the count of the numbers under 200 which are divisible by 200. So 18 ones are 18, I'm left with 2, then another one. So there are 11 numbers which are divisible by 18. When I'm talking about 9, it also has the divisibles, it has also those numbers which are divisible by 18. When I'm talking about 6, it also has the numbers which are divisible by 18. So my answer here would be 22 plus 33. This is a partial answer. I have to subtract once the number of common factors. The number of common factors are that of those numbers which are divisible by 18. 22 plus 33 makes it 55. 55 minus 11 makes it 44. So 44 is my final answer. Got it? 44 is my final answer. Moving on. If A and B are events with PA being 3 by 8, PB being 1 by 2, and PA union B, A intersection B being 1 by 4, find P A naught intersection P B naught. I'll tell you about one simple relationship. P A union B plus P A naught intersection B naught is equal to 1. Okay? The possibility of two events occurring together plus the possibility of neither of the two events intersecting is equal to 1. So after this equation has been established, my answer becomes very easy, because this is something which I need to find out. And this is something which I can derive from whatever information is given to me at the top. So to find out the value of PA union B, I have PA plus PB minus PA intersection B. It's as simple as this. I'll quickly put in the values. The value of PA is 3 by 8. The value of PB is 1 by 2. And the value of PA intersection B is 1 by 4. I'll calculate it. 3 by 8, I'll make all of them to be multiples of 8, or like I'll make the denominator the same. This is 4 by 8 and this is 2 by 8. Okay, the denominators are same. The calculation is getting easier for me now. 3 plus 4 is 7. 7 minus 2 is 5. So 5 by 8 is my answer. Okay, 5 by 8 is my answer. I hope it is very clear to everybody. So this was the entire chapter of probability. We have gone through multiple different concepts, multiple different concepts. The most interesting ones were taught somewhere in the end. Then we also talked about combinations, we also talked about permutations, and there was an array of different questions coming up. Okay, so I hope you understood. If there is any problem that you face, do write to us in the comments. Thank you.